Hello, everyone, and welcome back to this series of probability. Last time we started with the discrete random variables, and I said today we are going to look at some models that we will encounter in real life. Um, at the basis or the mother of a huge area of discrete probabilities is called the Bernoulli trial. So, what is a Bernoulli trial? The Bernoulli trial is an experiment that has exactly two possible outcomes. Yeah, I hear somebody in the back. He said this guy told us that probability is not about tossing a coin or rolling a die, and now all his examples about tossing a coin or rolling a die. Yeah, you may be right. I want to make the examples easy, but now for a Bernoulli trial that has only two possible outcomes, we usually call them success and failure. Success, by the way, doesn't mean something good. It may be the bad thing. It doesn't matter, whatever you call it. So, for example, remember when we said that we had three machines and they are producing stuff with different failure rates and whatever, and then I'm going to pick only one element at random and check it. It's either defective or non-defective, two possible outcomes, conforming to specs or not conforming to specs, acceptable, rejectable, on, off, yes, no, positive, negative, 0, 1. All of these are two possible outcomes, and we encounter that a lot if it's only one event and it has only two possible outcomes. If you want to express that mathematically, we usually refer to to P as the probability of success, and 1 minus P, sometimes we refer to it with the letter Q, is the probability of failure. And of course, it's either success or a failure, so the probability add up to 1. There is no negative. So these are valid. That's a valid random number, random variable, I mean. Okay, so if I want to represent the Bernoulli trial, I say, okay, my X random variable can either be 0 or 1. And the probability of X, of course, 1, we said it's the probability of success is P. The sum of the probabilities is 1, so this is 1 minus P. So the mean is so easy. 0 times that plus 1 times P, so it's P. The expected value of X is 0 times 1 minus P plus P equals P. Or P times 1 if you want. Okay. Now, what is the variance? I want you to stop the video and try to find the variance for yourself. And of course, the standard deviation is the positive root of the variance. But what is the variance? Remember we said the variance of X or sigma square of X, there are two ways to do it. Either to say it's the summation for all possible values of I of X sub I minus mu X square times the probability of X sub I, in which case I'm going to say 0 minus P. Notice mu is P. So 0 minus P squared times 1 minus P plus 1 minus P squared times P. If you expand, you will get P squared times 1 minus P, since 0 minus P is negative P, plus, and if you break that, you will get times P. Expanding again, you get P squared minus P cubed plus P minus 2P squared plus P cubed. You see that P cubed and P cubed cancel. You get P squared minus, so you get P, and then P squared minus 2P squared is minus P squared. You can write it as P times 1 minus P, and sigma X would be the square root of P times 1 minus P. Okay? I will go back and try to make sense of these like theoretical things, so to speak. But let's first do it the other way. Remember, we said we take x, the summation of x squared times p minus the mean square. Remember, we said if these numbers, especially if they are integers, you can say 0 squared times 1 minus p plus 1 square times p minus the mean square. So here, of course, this will get to 0, and this 1 squared times p is p minus p squared, same result, but easier way, faster way, okay? Now, so what do we say? So what can we see about that? Let's talk about even the variance. The variance is p minus p squared, okay? This is a function of p. So a very common should come to your mind, and you say, what value of p would make the variance maximum? You say, oh my God, why are we talking calculus here? So if I take the derivative of sigma squared with respect to p, I get 1 minus twice p. If I want to find an extreme value, I would equate, so I say d sigma square x by dp equals 1 minus twice p. To find the value of p that maximizes that, I would equate it to 0, so I get 2p equals 1, p equals 1 half. If I take the second derivative, right? If I take the second derivative, I get negative 2, meaning that's a maximum. This value would maximize the variance. Okay, think about it. If P, the probability of success is finding a bad part in your production. Notice here I said the success is finding the bad part. Remember, I said it doesn't have to be a good thing. Really, a good thing is to weed off the bad parts in your production. So if I consider P the probability of success, and I tell you P is 0.95, so only 5% of my production is bad, then on average, every 20 times you get 19 good parts and only one bad part. So the variability is very low. Most of the time you will get the failure, which is a good part, and only one in every 20 time on average, or 5 times in 100, you get a success. You see here the variability is very low. Variability meaning, you know, the variability is very low because most of them are good. So all the time you get good, and then one bad, good, one bad. So if the probability becomes 99% success, then the failure rate is only 1%. So every 100 units, you keep doing the experiment and the result is almost the same. So there is no variability almost. But what if it's a 50-50, like tossing a coin that many of you are bored of hearing? But if it's 50-50 and I say, okay, let me check. Oh my God, you get, for example, 2 heads, then 3 tails, then a head, then a tail, then it's all over the place. The variability is very high. And that's the meaning of the variability, is that usually variability in any like industrial system is our main or most ardent enemy. That's the enemy we want to get rid of. I don't want to have variability in my production. I want them all to be perfect, which is almost impossible, right? You can keep decreasing the the defective parts or the defective proportion, but you will never get rid of it. You can make it 1 in a million, 1 in a billion. You can, if some of you heard about terms like Six Sigma and continuous improvement and stuff, our goal is to, and that's the good thing about engineering, is that you are never satisfied with the result. You always want to get it better. So if you are a quality control guru, you want to have your production to be perfect. If you get it up to 99.999, you are still not convinced. I want to make it better. So you keep continually improving. And that's what is, about competing worldwide between different economies that they want to have larger market share. And the only way you do it by proving that your product is better than the other guy. Okay, we talked a lot about that, but that's the Bernoulli trial. I said the Bernoulli trial underlies many other uh, probability distributions. The next one, suppose I tell you, okay, I'm not leaving today until I find the defective part. And he said, okay, you can find it in the first element. I said, okay, that's the deal. Take it or leave it. I'm going to work for you until I find one. I weed off, I find one defective part. If I find it the first one, I'm going to throw it in the garbage, leave, and get my payday. That's a funny thing. I said, oh, but guess what? I may be working all day, like 24 hours, and I don't find anything. So what do you think? If you say yes, how do I describe that? You would say, well, that's an infinite distribution, right? Yeah, it's an infinite distribution, but let's try to find the probability of that. Of course, you cannot find it without experiments, so there is no zero here. What is the probability that you get it in your first trial, or your second, or your third, or your fourth, blah, blah, blah. Okay, the probability I get it in the first trial is P, right? You say, yeah. You select the first item, success is P, you find it, it's P. So if P is like 1.01, then every 100 days you find it on the first trial and go home and get paid the whole day. Neat, right? But what is the probability that you exactly get it on your second trial? You say the only way to do that is that the first is a failure and the second is a success. And you say, why did you multiply them? I say, because they are independent. If I find the first to be success or a failure, meaning it's a good item, that has nothing to do with the second one. The second one may be success or maybe failure, right? The probability is the same. And you keep doing that. So it's always going to be P to the n minus 1, where n is the number of experiment. I'm sorry, P times 1. So the probability of x can be now written as a function. I don't have to say this times that plus this times that plus to find the mean or the variance. No, I can write a function. It's not like the example we took last time of 2, 5, and 7, and that may be even more values of x. Here, what I can say is that the probability of x can be described as 1 minus p times n minus 1 times p, right? To get in the first trial, it would be 1 minus p to the 0, which is 1 times p. 1 minus p to the first, 2 minus 1 times p. So you get 1 minus p, and so on and so forth. Now, what is the expected value of x? Meaning, on average, how many times do you think I will get it? I will get a success if that's the case. Common sense would say what? Okay, I'm going to give you again the example you hate, tossing a coin. On average, how many flips of coin would you have to do until you get, say, a head, if head is the success? On average, I'm not saying it's guaranteed, but on average, sometimes it may take you long, sometimes you get it on the first trial, but on average, If you say 2, you would be right because it's 50-50, right? So one day, the perfect scenario is that one day I get tail, the other I get head, tail, head, or head, tail, head, tail. Of course, it won't be like that, but theoretically, that's what you expect. So once every 2 days, one half, right? Is it 1 over p? Common sense would say the e of x, but how can you do it? Remember we said it's the summation of x times p of x. So it's 1 time p plus 2 times p times 1 minus p plus 3 times p times 1 minus p square plus till infinity. Oh, I'm sorry, 1 minus p square. If I factor out the p, I will get 1 plus 2 times 1 minus p plus 3 times 1 minus p square plus till infinity. Right? What is that? How do I sum those? I'm going to do it in a very weird manner. I'm going to say, I mean, there are many ways to solve that, but I'm going to say it's p times 1 plus 1 minus p plus 1 minus p plus square plus till infinity. So I'm going to take one of those, one of those, one of the next. So that becomes p times 1 plus 1 minus p plus 1 minus p square plus till infinity plus. I'm sorry, I should have added that here. So let's forget about that. Plus, notice here I get 1 minus p plus 1 minus p square plus till infinity. And then I'm going to add to that 1 minus p quantity square plus 1 minus p cubed plus 1 minus p to the fourth till infinity, infinite series. Wait a second. P times an infinite series. So I'm going to say infinite series plus, if I factor 1 minus p here, the rest would be 1 plus 1 minus p, which is the infinite series, plus, and then I will factor out 1 minus p squared here, and times the infinite series, and so on and so forth. So that becomes the probability. If I take the infinite series out, let's call it S as a common factor. The first term would be 1. The second term would be 1 minus p. The third term would be 1 minus p quantity squared plus infinity, which is p times S squared, right? Because that's an infinite series. But what is this infinite series? What does it add up to? You learned about infinite geometric series, right? If I say 1 plus 1 half plus 1 half square, which is a quarter, you know that the sum would be 1 over 1 minus 1 half equals 1 over 1 half equals 2. Meaning if you keep add 1 and a half and a quarter and 1/8 and 1/16, in the limit you would reach 2. So that becomes P times 1 over 1 minus the product. Notice here I said 1 minus 1 half. Here I would say 1 minus P. That's the sum of the series, but it's squared. So I will get P times 1 over 1 minus 1 cancel minus negative. So 1 over P square equals 1 over P. Wow. Same thing. So the mean is 1 over p. That's common sense. if the probability of success, meaning if your failure rate is 1/10, I expect to get one every 10 day on average. If it's 100th, I will get one success every 100 days on average, and so on and so forth. So this is called the geometric series, and you see why we call it the geometric series. And you use it if you want to find the probability that you will encounter the first success on the nth day. So I can get, what is the likelihood that I get my first success in the 4th day or the 10th day or the 12th? You simply multiply p times 1 minus p to the n minus 1. The geometric series, and you will get one in the continuous, has what we call a memoryless property. What does that mean? Meaning, think about, again, just to make it easy, tossing a coin. What is the probability that you get a success on your first trial? Is 1/2. But what if I tell you, oh, I tossed a coin the first time and I get a tail? What is the likelihood that I will get a head the next time? Isn't it still 1/2? Yes, unless the coin is biased, right? Okay. Oh my God, it was a worse day. I got 10 tails in a row. That happens like once every, what, 3 years? If I keep doing that every day. But today it was so weird. I tossed a coin 10 times and I got a tail. What is the likelihood that I get ahead on the 11th trial, making sure that the coin was fine? It's still 1/2. It's still 1/2. So the process doesn't have memory. It doesn't remember what I got yesterday, right? And the geometric series has this property. Amazing, right? Okay, I'm gonna complete that with only one more distribution because it's very important, it's very common, but we are not going to do more today. And this is called the binomial distribution. Binomial distribution. He likes it because the binomial has the Pascal triangle. Oh my God. Yes, that's why I love it. Pascal is one of my idols, after Sir Isaac Newton, of course, on the top of the list, for me at least. Okay. The binomial distribution is if we repeat the Bernoulli trial, both starts with B, right? Bernoulli trial, n independent times. We'll understand what we mean by that. Keeping the probability of success unchanged. Then the Bernoulli, I'm sorry, the binomial distribution, or the Bernoulli, the binomial random variable, will give me the probability of having X successes in N trials. Wow, that's a long way to say it. Okay, the Bernoulli trial is a trial that has two possible outcomes, right? We established that. If we repeat that Bernoulli trial n independent times, what's the meaning of independent time? So for example, if I'm tossing a coin, I'm going to toss the same coin. over and over again. I'm not going to get another coin, so maybe one of them is biased or something. No, I'm going to use the same one. So the probability of success doesn't change. Or if I'm checking elements coming from a production line, I'll use the same production line. I'm not going to go to one factory today, excuse me, and a different factory tomorrow and a different factory the day after and assume this is that's not binomial. These are three different distributions, right? Three maybe Bernoulli or something that have nothing to do with each other. So how do I find the probability of X here? Well, let's think about it. Suppose, again, I'm using the tossing a coin for simplicity, but you can use any other example. If I'm tossing a coin, let's make it easy, 4 times. 4 tosses. What is the probability of getting, say, 3 heads, assuming head is the success? Hmm? Again, if you remember, we said when we listed them before, we said I can have head, 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 tail, or head, head, tail, head, or head, tail, head, head, or tail, head, head, head. There are 4 ways of getting 3 heads out of 4 tosses. Each one of those has a probability of 1/2, and we established that they are independent. So the probability so far is 1/2 times 1/2 times 1/2 times 1/2. But one of these halves is a failure, right? So I can write it as p cubed times 1 minus p. But there are 4 of them. Where does the 4 come from? So if I make that 2 heads, how many outcomes will that be? If you don't know, it's 6. How do I know? Because I use my Pascal triangle to the rescue. 4 times I'm here. So there are 4 ways of getting 1 head and 3 tails. 6 times you can get 2 heads and 2 tails. 4 times you get 3 heads and 1 tail, and only a single time you get 4 tails or 4 heads, right? That's only one way. So this is, I can write this as the probability of uh, x equals 3 and n equals 4. I want to write it like that first. It is 4 take 3, right? 4 take 0, 1, 2, 3. That's 3 heads or this is 3 heads and 1 tail. It doesn't matter if you count from the right or the left, times the probability P, that's the probability of success, raised to the power of 3 times 1 minus P times the probability of 4 minus 3. If there are 3 successes, then so to generalize, we are going to say the probability of X given N and P, meaning N trials, and the probability of success is P. It is N take X, P to the X, 1 minus P to the N minus X. This gives you the probability that you will get X successes in N trials if the probability of success is the same and if you only have 2 possible outcomes. If and only if P equals 1 minus P equals 1/2, I can use the binomial, I can use Pascal triangle. Like in this case, I could have said what? I could have said that the probability of 3 given 4 trials and 0.5, of course, if it's 1/2, equals this guy, which is 4, right? So I can get it from, okay? And what is the sum of these numbers? Remember we said it's 2 to the 4th, 2 to the 4th, which is 16. So there is one-fourth probability that I get three heads or three tails, it's the same, in 4 trials. Notice, I have 16 ways of getting a head or a tail, right? Or a combination of heads and tails that add up to 4. 1 and 4 is 5, 1 and 4 is 5, so that's 10, and 6 is 16, 2 to the fourth. And the probability, how many times I can get three heads? 4 times. So you divide 4 by 16. So if it's a 50-50, it's so easy to read it. If I run it 8 times, the probability of getting three heads is 56 over 2 to the 8, which is 256. So 56 over 256. If I'm running it twice, the probability of getting one head or one tail is 1 over 1 plus 1, which is 1/2. And you can see it works. But if the probability of success is not 1/2, you have to do the math. You have to do it this way. You can get this number, of course, from the Pascal triangle, but P would be different. If that's 0.4, then you say 0.4 cubed times 0.6. You can't get that from the Pascal triangle. The expected value of x here turns out to be NP, which makes sense. Why does it make sense? Because we said the probability of success in one trial is P. So if I repeat the trial n times and they are independent, and really they are, if I repeat it n times, I expect to get n times P. Meaning, if I toss a coin 10 times, I expect to get 5 heads and 5 tails. Not I guarantee. Remember, that's the expectation to get 5 heads and 5 tails. 10 times 1/2 is 5. And the variance of x is n times p times 1 minus p, which, as I said, some people would write it npq. And again, the maximum variability is in the coin when the probability of success is 0.5. Again, if you take the derivative of that, you will see that the maximum occurs at p equals 1 minus p equals 1/2. Okay, so we did the Bernoulli. We looked at the geometric, which has the memoryless function. It's getting like Alzheimer like me, and the binomial distribution. We'll maybe touch on 2 more distributions next session, and then we'll move to continuous distributions. Okay? Thank you very much for your time and hope to see you soon.